Welcome. This is Precalculus, section P5, Factoring Polynomials. So in previous sections, we talked a little bit about multiplying polynomials together to get some sort of sum of a bunch of terms. With factoring, we want to start thinking backwards, okay? On our objectives for factoring, so we're going to look at many different types of factoring techniques. First, we're going to factor out the greatest common factor, then grouping, then trinomials, and then some of the special cases like the difference of squares, perfect square trinomials, and the sum and difference of cubes. Then we'll finish by talking about a little bit of a general strategy for what you should do to factor polynomials as far as you can. And finally, we are going to factor algebraic expressions containing fractional and negative exponents. Okay, so factoring a polynomial expressed as the sum of monomials means finding an equivalent expression that is a product. So here is a polynomial that is the sum of two monomials, right? We have 10x squared and 15x. What we can do is we can change the sum of the monomials into an equivalent expression that is a product by factoring out the 5x. Okay. We'll get back into a little bit more in depth with what we're actually doing here, but we're basically dividing out the 5x and we're making this a product. If I were to distribute this again, I would get 10x squared, 5x times 3 is 15x, right? That's where that's where the sum of the monomials, that's where we started, right? So if I multiply the two factors together, I should go back to where I started from. We are going to be factoring over the set of integers, which means that the coefficients in my factors are integers, right? We are not going to factor over rationals, okay? Or irrational numbers. We're always going to be factoring out integer terms. If we reach a polynomial that cannot be factored using integer coefficients, it's called irreducible over the integers, or better, prime. Okay? Our goal for factoring a polynomial is to use one or more factoring techniques until each one of the polynomial's factors, except possibly for a monomial factor, is prime or irreducible. In this situation, we said that the polynomial is factored completely. So we're looking to break this down. Let's clear this out. We're looking to break this expression down into as many possible different products as we can. And then when we're done, we can say it is factored completely, right? Because there's nothing else I can take out of 5x, and there's nothing else I can take out of 2x plus 3. Okay, so let's start with the most basic techniques, all right? So this is going to be our first step with any factoring product, is we're going to look for the greatest common factor, the GCF. And this is an expression of the highest degree that divides each term of the polynomial. The distributive property in reverse can show this, okay? So again, if we have AB and AC, we factor out an A because the highest degree, or sorry, the common factor is the most that we can take out is A to the first power, because A is common to both of them, and the smallest degree of A is 1, so that's what I can take out of each factor. I'll talk a little bit more about that later when we look at the fractional exponents. Okay. But we should be pretty clear here that both of these have an A, so I can divide out the A. Okay. Let's try this with actual numbers. So we have 18x to the third and 27x squared. Okay. The biggest exponent that divides both of these is x squared, okay? Because that is the smallest exponent that is common to both of them, okay? So I can take out an x squared from this expression. I also can take out a numerical factor. the biggest number that goes into 18 and 27 is 9. So I can take out 9x squared. What's left? Okay, well, if I take 18x to the third and I divide out a 9x squared, I subtract the exponents. 18 divided by 9 is 2. It leaves me with 2x. And 27x squared divided by 9x squared is a 3. This expression is now factored completely because 2x and 3 have no common factors. 9 times x squared is already multiplication, so it is already factored out. Okay? And we use the greatest common factor to simplify this. Here, with this expression, the greatest common factor is a binomial factor of x plus 3, because both of these expressions have x plus 3. Right? If this was just another letter, like say b, right, x squared times b plus 5 times b, I would factor out the b, and this would leave me with x squared plus 5 inside. Okay? This idea is the same here, even with a binomial factor. I can factor out the x plus 3, and I'm left with x squared plus 5. Okay? It's not squared. Okay? That's not what's happening here, right? We are factoring this out and then using the distributive property backwards to write this as the product of two factors. This was x plus 3 times x squared, x plus 3 times 5. Now it's x plus 3 times both x squared and 5, x squared plus 5. Okay? So these both expressions mean the same thing, right? If we were going to distribute, we'd have the x plus 3 times x squared, x plus 3 times 5, which is exactly what we have here. Okay? Let's do our checkpoint problems. Same idea here. In the first one, I can't factor out a 4 because 4 doesn't go into 10, but I can factor out a 2, and the smallest exponent with the base that's common to both, so 2x squared. And that's left with 5x minus 2. With this one, I can factor out the binomial factor of x minus 7, and I'm left with 2x plus 3. Okay? And this idea right here, with the second example before, and this example in part B, leads us to the technique of factoring by grouping. So some polynomials have only a greatest common factor of 1. However, by suitable grouping of the terms, it still may be possible to factor these expressions. Okay? This example, this process is called factoring by grouping. Here is a polynomial. It does not have a common factor, right? X to the third, these all have a common factor of x, but this one doesn't. These two have a common factor of 4, these two have a common factor of 3, but this one is just a 1, so it doesn't have a numerical common factor. So basically, just looking at this, I would not be able to use my factoring technique that I previously used. But what I can do is I can look at both of these two separately. Okay? With these two, they do have a common factor. Their common factor is x squared. And left over would be x plus 4. These two have a common factor. It's a positive 3. And left over is x plus 4. Now I can factor out the binomial factor of x plus 4 times the leftover x squared plus 3. Not sure if this actually works. Check it with FOIL, right? First would be x to the third. Good. Outside would be 3x, that's this one. Inside would be 4x squared, that's this one. And 4 times 3 gives me 12, which is that one. So this does actually work. And if you do factor correctly, it should always FOIL back together. Let's try that again with our checkpoint problem. Group these two and these two. X squared can come out of the first terms, which leaves me with x plus 5. Okay, and if I just factored out a 2, I would be left with negative x minus 5, which is not the same. In order to factor out the binomial factor, both the binomial factors have to be exactly the same. So what I can do is factor out a negative 2, which means we with x plus 5, negative 2 times positive 5 is a negative 10. Okay? And now the binomial factors of x plus 5 are the same, and I can factor them out to x squared minus 2 to give me a product of two binomials. Okay, so those are the first two techniques we looked at there, which is factoring with the greatest common factor and then factoring with grouping. Next, we are going to factor trinomials. Okay? The main way to factor trinomials is with trial and error, guess and check. Okay? I'll also go through something called the AC grouping method. AC grouping method. Okay? So we'll get to this in a second, but first, a general strategy for factoring ax squared plus bx for c is first we assume that there's no greatest common factor, because if there is, that is the first thing you should do, is to take that out. When we FOIL two binomials together, the first terms multiply together to give you that. The last terms multiply together to give you c. Only thing that is combined is the inside and the outside terms combined to give me the middle term. So we should pretty much guess numbers whose multiply together to give me the first term, these numbers that multiply together to give me the last term, and try to find the right numbers, the right factors, the right product to make the sum the inside. And if it doesn't work, the polynomial is said to be prime. Let's take a look. Factoring a trinomial is easier when the leading coefficient is 1, right? Because I know what my first term is going to be. If I write my product here, there's only one thing that multiplies together to give me x squared, x and x. Okay? X times x is x squared. What we need now is the factors of 8 that add to 6. Why do I say add? Because the only way to get a positive 8 by multiplying these two numbers, the two last numbers, the only way to get a positive 8 is to have them both be positive or both be negative. Okay? So the sum has to be a positive 6, which means if both sides are the same, you are going to add the two things together, and the only way to get a positive is if they are both positive. So if we look at the factors of 8, 1 and 8, 2 and 4, and we add them together, we get 9 and 6. So 9 does not work, but 6 is the term that I want. So we want a positive 2, a positive 4, check your answer, FOIL it together, and you get x squared plus 6x plus 8. Now, this might be a lot of steps for a problem that is a little bit simpler, but it is a good idea to get the idea down for the easier problems. So shortcut here is I want the factors. I like to read this from right to left. The factors of 40 that add to 13. So if I can't think of it, list the factors of 40. That's 1 and 40. If I add those together, I get 41. No good. 2 and 20. Add those together, you get 22. No good. 3 does not go into 40, but 4 does. 4 and 10. And that's 14. It's close, but it has to be exact. And 5 times 8, which is 13. So we want x plus 5, x plus 8 are my two factors. And it doesn't matter which way you write them, right? commutative property says I can multiply this either way that I want. It does not matter as long as the terms inside the parentheses are correct. Okay. Is there a way to eliminate some of the combinations of factors for a trinomial whose leading coefficient is 1? And we just mentioned this. Is if this is a positive, right? These two things are going to have the same sign, and it's going to be that sign. If this is a positive, the only way we can multiply together to get a positive is if the signs are the same, and it's going to be that sign. So I know both terms are going to be negative. If it's negative, I know they're opposite signs, and I'm going to get the bigger number to be positive here and negative there. Okay, so we just know that the two factors are going to subtract and give me factors of 18 that subtract to give me 3, 6 and 3. The factors of 99 that subtract to give me 2, 9 and 11. Okay, 11 is negative because I want a negative 2, not a positive 2. All right, and we can think about this as we're trying to guess our factors to build our factors. Let's try one like that. The factors of 18 that subtract and give me 3. So the factors of 18 that subtract and give me 3. Let's see, 18. I want a positive 3, which means the bigger number has to be positive. So how about negative 1 and positive 18? When I multiply those together, I get negative 18. When I add them together, I get a 17. Oh, good. Well, what about negative 2 and a positive 9? Well, when I add those together, I get a 7. That's no good. That's no good. What about negative 3 and a positive 6? Well, look at that. I get a 3. So I want x minus 3, x plus 6. Okay. And if you see this right away without having to list all the factors down, then that's a good thing. Okay. Let's go one more for these. Nope, I don't want to do it. Okay. Next, this would be the AC grouping method. Okay, so factoring a trinomial whose leading coefficient is not 1. Okay, we have a couple ways that we can do this. Right, I can try to guess. Okay, the factors of 8 are going to be the lead terms. So I could have 8x and x, or I could have 4x and 2x, right? Factors of 8 are 1 and 8, 4 and 2. Okay, that is how I have to start my expression. 3 is prime, which means that there's a 1 and a 3 going to go in one of these two places. Well, I could try like this, and that gives me 8 times 3, and the signs are going to be different. So I can put a negative 3 and a positive there because I want the bigger product to be negative because I want my sum to be negative when I FOIL this together. 8 times 3 gives me a negative 24 plus 1 gives me 23. So that's no good. I could try it the other way to give me 8 and negative 8 and a positive 3, which gives me 5. It didn't work, so that means that method, or that factor pair is no good. Okay? So what I can do now is I can try to put the 1 and the 3 in this one. And I can see that 4 times 3 is 12. 2 times 1 is 2. Negative 12 and a positive 2 give me a negative 10. Right? So what I just did was 8x squared, negative 12x, positive 2x, and a negative 3. Okay? So by foiling this together, or by guessing the factors and foiling them together and sort of making the factored expression equal my original expression, I can successfully factor it. That is called the guess and check method. Okay? Let's try this. AC grouping. That's A, that's C. 8 times 3 is negative 24. So let's find the factors of negative 24 that combine to give me negative 10. Well, negative 24, right? One has to be positive, one has to be negative. I want the sum to be negative, so I want the bigger number to be negative. So that's that. Add those together, I get negative 23. No good. I'm looking for negative 10. 2 and negative 12 is a negative 10. Boom. Okay. Now the difference here is I am not sure what the first factors are be. Unlike this previous example, right, it's not just going to be x and x, okay? So now what I do is I take the middle term and I split it into these two. So I rewrite my equation as 8x squared plus 2x minus 12x minus 3. I didn't factor anything yet. All I did was take the negative 10 and I split it into 2 and negative 12. Now I factor with grouping. These two first. Factor out a 2x. And we're left with 4x plus 1. Here, factor out a negative 3. And we're left with 4x plus 1. These two terms are the same, the binomials are the same, and I can factor them out to be left with the same expression that I got up there. 4x plus 1 times 2x minus 3. Okay? I usually tend to try this method first to just see if I can see the factors. If you get stuck, you can always fall back on the AC grouping method. The problem with this method is that A times C, we're multiplying two things here, so A times C can give you a large number very quickly. Let's try the checkpoint. Okay. Let's see if we can do this with the guessing method. So I'm going to list out my factors here, 1 and 6, 2 and 3, and the only factors I have there are 1 and 7. Both signs are different because I haven't multiplied to give me a negative. The bigger product is going to be positive. Here would be my guess. Well, 6 times 7, that's going to be too big to give me 19. So I'm going to start with 2x and 3x. 2 times 7 is 14. No, that doesn't work. Now let's just go through that. 7 and 1, so that's 14. Inside pair is 3. There's no way I could put a positive and a negative there and have them combine to give me a positive 19. But 21 minus 2, a positive 21 and a negative 2, positive 21 because that's the inside pair and the outside pair, gives me a positive 19. So this is the factored expression. Again, if I wanted to, I can multiply 6 and negative 7 and find the factors that subtract to 19, split up the middle term into whatever, and factor by grouping. Let's try this one with two variables. Okay? So the first two terms are going to have a product of 2x squared. Well, since 2 is prime, I know it's going to be 2x and x. The last two terms are going to have a product of 3y. So that is going to be 3y squared. So that's going to be 3y times y. Okay, that's the only way to get 3y squared. 3 is prime. Also, I can be negative 3y times a negative y, right? Negative times a negative gives me a positive. And in fact, that's the one that I want, since that term is negative. And I want it to be a negative 7. So I'm going to put that there. So the 2 and the 3 multiply together to give me 6, and the negative y there for 1 more. If we FOIL this out, you would see that these multiply together to give me my original expression. Let's try another little checkpoint problem. Let's go back to the AC method one more time. Okay, so we're just going to work with the coefficients here for a second. So 3 times 4, that's going to be 12. Okay, I want them to add to be negative. That means they're both going to be negative. So negative 1 and negative 12 add together to negative 13. Oh, look at that, first one. Okay, so that's 3x squared minus xy minus 12xy plus 4y squared. And why did I put xy? Because that was what the middle term, that's the variable of the middle term. And all I did was I split that negative 13 into these two factors that did the thing I wanted it to, right? The product that adds to negative 13, negative 1 and 12. Factor by grouping, I can factor out an x in the first expression to give me 3x minus y. In this second expression, I can factor out a negative 4 to give me negative 4, negative 4y, right? They both have a y. And I'm left with 3x minus a y. Then I factor out the 3x minus y, the binomial, and I'm left with my factored expression. 3x minus y times x minus 4y. All right, so now that we have the basics, let's do some special cases. So first is called the difference of two squares. And the method for factoring these by reversing the special product of the sum and the difference of two squares. So if a and b are real numbers, the variables or algebraic expressions, then, oh, this is important, they could also be, we'll see this maybe later, they don't just have to be real numbers or variables. They could actually be algebraic expressions. If we have something squared minus another something squared, it factors into a plus b times a minus b. And the reason why that works is this is a positive ab, this is a negative ab, and that middle term goes away. So let's factor this. The way I can tell whether or not I'm going to use this technique is are both of these terms perfect squares? Yes, x squared is a perfect square. It's x times x. Yes, 4 is a perfect square. It is 2 times 2. So this factors into x plus 2, x minus 2. And if I FOIL this together, I can see that that middle term definitely goes away. This expression, the sum of two squares, it's not factorable across real numbers. Because right here, in this expression, we're looking at for the factors of 4 that subtract, there's no middle term. So the factors of 4 that subtract and give you 0. So that's 2 minus 2, that's 0. Here, I would want the factors of 4 that add to 0, which there are none. Factors of 4 are 1 and 4, that's 5. 2 and 2, that's 4 again. Okay, so this not factorable only, and that's why it only says the difference of two perfect squares, not the sum or difference, right? Just the difference. When there's a number in the front, we can factor this in the same method. Okay, we just check, are both of them perfect squares? And they are. It's 9x and 7, 9x plus 7. Doesn't matter which one you start with, right? Because the commutative property, we can go either way. Our checkpoints, x minus 9, x plus 9. The difference of two perfect squares. With a number in the front, it just make sure I put a number in the front of the x. 6x times 6x is 36x squared. 5 times 5 is 25. So those are my two factors. 6x minus 5 and 6x plus 5. Okay. Now one thing to note is that polynomials are factored completely when it's written as the product of prime polynomials. Both of these are prime. You cannot factor them anymore. Okay. To be sure you have factored completely, check to see whether any factors with more than one term in the factored polynomial can be factored further. If you can factor more, do it. Like this problem. So x to the fourth is a perfect square. It is x squared times x squared. 81 is a perfect square. It's 9 times 9. So I can factor this with the technique that I just used. Okay? x squared plus 9 is prime. You cannot factor in anymore because it is the sum of two perfect squares. But x squared minus 9 is factorable more. It factors into x minus 3, x plus 3. So the point of this question is to see that once you do the first step, maybe you can do a little bit more. Okay? And my checkpoint problem is the same idea. 81x to the fourth is 9x squared times 9x squared. 16 is 4 times 4. The plus, the sum of two perfect squares is not factorable, but the difference is. And we get my new expression right here as the product of prime factors. Okay. Next, we have my perfect square trinomials. So this technique is obtained by reversing the special products for squaring binomials. Trinomials that are factored using this technique are called perfect square trinomials. So again, you're looking for something to be a perfect square here, something to be a perfect square here, and you just got to check this middle term. If I have a and b gotten from my perfect squares, if I multiply these together and then multiply by 2, does this is this middle term 2 times a times b? And why is it 2? Because, right, whoops, a plus b squared is a plus b times a plus b. And when we FOIL this together, we get a squared, ab, and another ab, and then b squared, right? So there's 2 ab's. If this is a positive, this is positive. If this is negative, that is negative as well. Okay? Little trickier to recognize than a perfect square binomial, right? Because we're already thinking it has to be something because it's a binomial. The perfect square trinomials are just a little bit harder to recognize. How I can do it is look at the first term, look at the last term, and they're squares of monomials or integers. And the middle term is twice the product of the expression being squared in the first and last terms. So that is a perfect square. That is a perfect square. So I can try this technique. It would be x positive plus 3. So is x times 3 times 2 more 6? Yes. So that means that this is x plus 3 times x plus 3. Also, the factors of 9 that add to 6 are 3 and 3. But I don't want to write it this way. I want to be more efficient. I want to write my perfect square trinomial as a binomial squared to show that it is a perfect square. Okay? And it doesn't have to have a 1 in the front. It could be like this one. Big hint, oops. Big hint is that that is a perfect square and that is a perfect square. So I would definitely start with this technique and see if the 60 works out. This would be my first guess, right? I would say, okay, this could be 5x minus 6. It could be this. Does it actually work? 5 times 6 is 5 times negative 6 is negative 30 times 2 is negative 60x. So this does work. So that is a perfect square trinomial. My 2 checkpoints, perfect square, be x plus 7 squared. Does it work? X times 7 is 7x times 2 is 14x. Perfect square, we would have 4x plus 7. If this works, then 4 times 7 times 2 is 56, which it is. Okay. Now, these two techniques, perfect square trinomials and my difference of two perfect squares, are pretty common and pretty well known. The next one is a little bit different. Okay, so this is going to be the sum or the difference of two perfect cubes. And to factor the sum and the difference of two perfect cubes, I like to use the acronym SOAP to help me remember what to do with the signs in the expression. So SOAP stands for same signs, opposite sign, always positive. Same sign, opposite sign, always positive. Okay. And then when I look at the expression for factoring the sum of two cubes, right? First of all, I know I'm going to have to use this technique because I have a perfect cube plus or minus another perfect cube. And then I do have to remember how this expression works. It's a plus b times a squared, ab, b squared. The signs, however, are what the acronym can help me with. Same sign, opposite sign, always positive. Same sign, opposite sign, always positive. There's three signs in every expression here. Okay. Notice that there's not a 2 there. Okay. Which means that this expression, a squared minus ab plus b squared, is never factorable further. If you can factor this after factoring using this technique, you did something wrong. Okay? So it's never factorable. We can solve it, and we'll see that it'll have an imaginary answer, usually having to do with a radical 3. For a difference of two perfect cubes, with a minus there, think about what's going to happen. Same sign, opposite sign, always positive. Okay? Negative, positive, positive. Might seem weird that there's so many positives in this, but if you were to distribute this, 1, 2, 3, 4, 5, 6, all those middle terms, except for the first term and the last term, they would all cancel out. Okay, and that's why this actually works for factoring. To recognize this, you need to realize that both terms must be perfect cubes. X to the third is a perfect cube. It is x times x times x. 8 is a perfect cube. It is 2 times 2 times 2. Okay. We'll get to the signs in a second. The next part of this expression, if this is a and this is b, it's always a squared, ab, b squared. For the signs, same sign, opposite sign, always positive. Okay. Same sign, opposite sign, always positive. A and b, if this is a to the third and this is b to the third, right? We just sort of ask myself what times what times what 3 times gives me x to the third, and then I can build the rest of the expression from there. I could have a number in the front. As long as it's a perfect cube, we can use this technique. 64 is 4 times 4 times 4. 125 is 5 times 5 times 5. So this turns into 4x, same sign, minus 5. Now, don't get tricked up here. The first term is this whole thing squared. So it's 16x squared. The middle term is 4x times 5. Don't worry about the sign. Don't say 4x times negative 5. It's just 4x times 5. So that's 20x. And then squared is 25. Same sign, opposite sign, always positive. Okay? So you could have gotten tricked up if you put 4x times 5 and said, or negative 5 and said, oh, that's a negative 20 in the middle. That's not the way this technique works. This technique works by remembering the acronym SOAP, so that way you can factor this expression. Again, ask yourself, are these perfect cubes? X to the third is a perfect cube. 1 is a perfect cube. It's x, same sign, opposite sign. Multiply these together. Always positive, square the last term. Okay. 125x to the third, that is 5x. 2 times 2 times 2 is 8. Same sign. Square it. Square the first term. 25x squared. Did I put an x squared back up here? Yeah, okay, good. 25x squared, same sign, opposite sign, 10x, 5x times 2, always positive with the last term squared, with 2 squared. Okay. And that is my general technique for perfect cubes. Okay. So let's talk more of a general strategy. There's a lot of different techniques that we just went through in this section so far. We factored out a greatest common factor. We talked about grouping. We did polynomial or trinomials. Then we talked about the special products, difference of two squares, perfect square trinomials, and now we just did the difference of cubes. So you got to put all these together, and you want to select the right technique to use quickly. Okay? And you can do that by looking at how many terms are in the expression. Okay? And of course, the order of the factors does not matter. So basically what you want to do first, okay, here's a general strategy. The first thing you want to do, every time you're trying to factor a polynomial, ask yourself, is there a common factor? Does it have a GCF? If it does, take that out first. It'll make the problem easier. The numbers will all get smaller inside, makes it easier to factor. And you're already taking a bunch of the stuff out that could be confusing. Okay, so that's the first step. Always the first step is take out the common factor. Step 2, determine the number of terms and try one of the techniques. If there are 2 terms, is it a difference of squares? Is it the sum or the difference of cubes? If it's one of these, then use that technique. If it's not one of these 3, you probably can't factor it anymore. Okay, so take out the GCF and then that's it. Okay? Is there 3 terms? Then see if it is one of these 2. If it is not, then factor by trial and error, right? Or the AC grouping method. Okay? If it is 4 terms, factor by grouping. Okay? Those are my techniques for now. Later on, we'll see that there are other techniques that we can use, like guessing a possible rational root and checking to see if it works with synthetic division. But for now, 4 or more terms, we're just going to stick with the grouping technique. Finally, we're going to see if any factors, once we factor one time, we're going to see if any factors with more than one term in the factor polynomial can be factored further. And if we can do it more. So, this expression, where would I start? I have to factor out the greatest common factor, which is an x, which is a 2x. Right? We want to factor out everything as possible. That leaves me with x squared plus 4x plus 4. Well, that's great because this happens to be, that's a perfect square, that's a perfect square. Let's see if this works as a perfect square trinomial. That would be x plus 2. X times 2 is 4. So this does factor as a perfect square trinomial. So what do? I factor out the greatest common factor, and I factor the piece that was left over. Let's try it again. Common factor would be 3x, and we're left with x minus x squared minus 10x plus 25, which perfect square, 3x, x minus 5 squared. X times 5 is 5x times 2 is 10. So that works. This has been successfully factored. Okay, so we've probably seen a lot of these types of problems in the past. Let's go through a few problems that might be a little weird, like this one. Okay, so first, step 1, is there a common factor? Well, we have x squared, 25, 8, 16. We got some x's, nothing, and an a squared. So this is not, it doesn't have a GCF. So again, how many terms does it have? If we go back to our technique sheet here, right, it's got 4 terms. So if we have 4 terms, try factoring by grouping. Okay, so I'm going to group these two, but they don't have anything in common. I can group these two and have an 8 in common, but that doesn't really help me. But maybe if I rearrange this and grouped it a little bit differently, something could happen. And if I look carefully at this, one of these terms is kind of not like the other ones. That term. So let's rearrange this using the commutative property. And I say x squared plus 8x plus 16 minus 25a squared. Okay? Now, normally when we do grouping, we look at 2 terms, but I noticed something. That is a perfect square, and that is a perfect square. So I can actually factor this as x plus 4 squared. Well, this term in the back is actually a perfect square as well. It is 5a, the whole thing squared. And now I have a perfect square because it's x plus 4 times x plus 4. I have a perfect square because it's 5a times 5a. This happens to be now the difference of 2 perfect squares. So if we recall the difference of 2 perfect squares, it factors into a plus b times a minus b. And remember that we said that a and b didn't just have to be a number or a variable. It could also be a polynomial. So if this first thing squared is a, that is what x plus 4 is. So we have x plus 4, that's a, plus b times a minus b. And now I have successfully factored this polynomial into 2 trinomials multiplied together. Okay? Probably wouldn't have seen this right off the bat if you were just looking at this, but if you think about the order of the techniques that we just talked about, 4 terms, factor with grouping, I tried to factor it first, I rearranged the expression, factored it one time, and then another factoring technique fell out after I factored it the first time. Let's try one more of those. Again, rearranging this gives me x squared plus 20x plus 100 minus 36a squared. These three, x squared is a perfect square, 100 is a perfect square, so that's x plus 10 squared. This one becomes 6a squared. And now this is the difference of perfect squares. X plus 10 plus 6a, x plus 10 minus 6a. Using the same technique from before. Okay. So if that didn't blow your mind, this one should be fun. We can factor algebraic expressions containing fractional and negative exponents. Technically, these are not polynomials, but we can continue to simplify them using the same techniques. And let's just recap again how we take out a greatest common factor. Okay, let's keep it nice and easy. Let's go 2x squared plus 4x. If I wanted to factor that expression, I would notice that they have a number in common, a 2. They also have a variable in common, an x. So I had to take the variable out, and I chose to take out the smallest degree of the common variable. The way I get what's left over is with division, I subtract the exponents. So you can divide out the number, right? And then instead of x squared left over, I have x, because 2 minus 1 is 1. Here, I have x to the first power. I'm taking out an x to the first power. That leaves me with x to the 0 power. So I don't have a variable anymore. And then 4 divided by 2 is 2. Now that might seem really basic, and it was. We're going to use the same idea for expressions that are much more complicated, like this one. Okay? So, when you see an expression involving a fractional and a negative exponent, don't freak out. Look for the common factor. Both of these have a common factor of x plus 1. This has an x, this doesn't have an x outside, right? The common factor is this binomial expression. So I'm going to factor it out, right? The point of this is to change this into something multiplied together. Okay, so this is what we're going to do. I'm going to factor out the x plus 1. But just like we just said, you can only factor out the smallest degree of the exponent. Well, this is a negative 3 over 4. This is a positive 1/4. Negative 3 over 4 is smaller than 1/4. So that is what I'm going to factor out. And I'm going to be left with something inside these parentheses. Well, I took out the whole thing, right? I started with negative 3 over 4. I'm going to subtract exponents in order to divide it out. Negative 3 over 4 minus a negative 3 over 4 is 0, right? I factored out the whole thing. But that's left over, right? And if I were to distribute this back in, right? X times this gives me this. Okay. What about the other one? This one. I'm factoring out a negative 3/4 of this factor. Okay. So I'm starting with 1/4. I'm going to factor out a negative 3/4, which means I subtract. So 1/4 minus a negative 3/4 is a 1, which means that we have x plus 1 to the first power, which means we do not need any parentheses to raise something to the first power. It is just itself. And now I have a like term. So we have x plus 1 to the negative 3 over 4 power times 2x plus 1, because I can add those together inside those parentheses. If you recall from our section with exponents, you are not allowed to leave negative exponents in a simplified expression. So we're going to take this negative exponent and we are going to move it to the bottom of a fraction. And from that same lesson, hopefully you recall that you cannot leave a fractional exponent in the denominator. So we're also going to rationalize this to make it not a fraction anymore. So I need to put another x plus 1 to the 1/4 power, which leaves me with 2x plus 1 to the first, but I don't need to write that, times x plus 1 to the 1/4 power over x plus 1. 3/4 plus 1/4 is 1. Now, this is simplified and rationalized. That is probably the answer that your homework on Math Excel will want you to type in, but this is the more correct version of that answer. Let's try that again. Common factor, x minus 1. I can only factor out the smallest degree of that common factor. The smallest degree is negative 1/2. And I'm left with an x there, 1/2 minus negative 1/2, right? Because when I factor out something, I'm going to subtract the exponents. So I'm going to start here. I'm going to subtract negative 1/2. That gives me 1. And I'm not going to write the parentheses to the first power. Again, this gives me 2x minus 1 times this term, which I'm going to make a positive exponent, whoops, by moving it to the bottom of a fraction. And then I'm going to rationalize it by multiplying the top and the bottom by x minus 1 to the 1/2 power, which turns this into just x minus 1. So let's do another one of those, just because I have a feeling that this is probably the more complicated problem for this section. Again, what do these two have in common? They have a 4x minus 1, but I can only factor out the smallest degree. That's that one. What's left is a 1. I factored the whole thing out, minus a third times this degree minus what I took out. 3 over 2 minus 1/2 is 1. Now we just got to clean up the inside here. So this becomes 4x minus 1. I have a positive 1/2. I don't need to move anything to the bottom of the fraction, which is nice. But I'm left with a stupid fraction here. So that's 1 minus 4 over 3x plus 1/3. I have to combine these two right here. So we have 4x minus 1 to the 1/2 power. 1 plus 1/3 is 4 over 3. Well, I'm not done yet because this expression still has a GCF. It has a common factor. So I can factor it out. And I'm going to factor the negative out. And because of the commutative property, it doesn't have to go here. That would look weird, right? It's just a multiplication term now. So I can move this all the way to the front. So my final expression is negative 4 over 3 times, let's put this one first too. What's left over there is x plus 1, and then 4x minus 1 to the 1/2 power. That is simplified, no need to rationalize. Oh, whoops, little mistake. Now 4x minus 1. Minus minus gives me my plus. Okay, that is simplified, and no need to rationalize because there's no negative exponents. Okay, I think I have a few of these. Let's do no. Okay, let's finish with this one. This one has two different types of common factors. Both terms have an x minus 5. Both terms have an x plus 5. So let's factor out an x minus 5 and an x plus 5 from both of these expressions. But I can only factor out the smallest degree of each one. So x minus 5 has a negative 1/2 and a negative 3 over 2. I can factor out the smallest one. X plus 5 has a negative 1/2 and a positive 1/2. I can factor out the smallest one. Okay. Now what's left over? Well, I factored out all of the x plus 5, so it's x minus 5 to some power. Negative 1/2 minus a negative 3 over 2 is 1. Minus, because there's a minus there. What's left over in this expression? I took all of this out, so it's just 1/2 minus the negative 1/2, which is 1 as well. Distributing that negative gives me, let's write this out. So that's x minus 5 to the negative 3 over 2 power, x plus 5 to the negative 1/2 power times x minus x goes away. Negative 5 minus a 5 gives me a negative 10. So my expression is negative 10 over x minus 5 to the 3 over 2, x plus 5 to the positive 1/2. Rationalizing this gives me x minus 5. I need another half to make that something that is a integer. And I need x plus 5. I need another half there. right? I have to do this to the top and the bottom, and this is going to finish by being a little ugly, a little complicated. So my answer, this is my simplified answer. It's just not rationalized. So my full answer, that is both simplified and rationalized, would be negative 10 times x minus 5 to the 1/2 power. X, oops, I didn't put the 5 there, x plus 5 to the 1/2 power, all over x minus 5 squared x plus 5 to the first. Again, an ugly, ugly answer, but it is factored, it is simplified, it is rationalized. And that was section P5, factoring polynomials.